Let's look at this problem. Note here, if a system has infinitely many solutions, what that means is that when you convert the system to a matrix, you will have a row of all zeros. And if you have that, then that's simply saying that we're going to have infinitely many solutions. That's one way to get infinitely many solutions. The other way to get infinitely many solutions is when you have the number of unknowns outweigh the number of equations. And I have that as a theorem here in this section. If you do have the infinite solution set, you must solve for that um, infinite solution set. So let's convert this to a matrix. Our goal for Gauss-Jordan is to get ones along the main diagonal and then zeros everywhere else. To do that, we consider uh, the columns first. So we start with column 1, get a leading 1 at A11, and then get zeros below it. And then we start after that with column 2, and we go to A22 to get a 1 there and get zeros above it and below it. And then after that we go to column 3, and we want to get a 1 at A33 and get zeros above it. So to get a 1 here where this 3 is, I can do one of two things. I can divide by 3 for row 1, or I can interchange rows 1 and 2. I'm just going to divide by 1/2 on row 1. So it gives us 1, -1, 2, two there. Just rewrite rows 2 and 3. Now we use A11 to get zeros below it. To do that, we say negative times row 1 plus row 2, and then -5 times row 1 plus row 3. Row 1 stays the same. So this is 0, 3, -3, and 3. Here we get a 0. Now we're saying -5 times row 1 plus row 3. So that's a 0. Then we get 5 minus 8, -3. -10 plus 13 is 3. And then -10 plus 7 is -3. Now adding row 2 to row 3 would just cancel out row 3. So that's the statement here. That's what I mean. We have an entire row of zeros. So that tells us that we're going to have infinitely many solutions. Now I'm going to keep on reducing this. I'm going to get still a 1 at A22. So this becomes 1/3 times row 2. So now we're going to use that 1 at A22 to get a 0 above it. We can do that by just simply adding row 2 to row 1. That's about all we can do there for Gauss-Jordan. We can't go any further because when you look at the main diagonal, the point of concern is where you have a 0 on the main diagonal. Where that 0 is, that variable becomes the floating parameter. So we'll say let here z equal to t, or a, or whatever you want to call it. I think I called it here a. But notice here that if there is a 0 on the main diagonal for that position, for that column, you cannot reduce those terms any further. You cannot get zeros here above where this 0 is here on the main diagonal. So let z equal to a. Since I used a, you can use any letter because letters are dummies and not humans. So you can say call whatever letter you want. You just call it out of existence because you have that authority. It's a mathematical authority and it's called the axiom of choice. The axiom of choice. But anyway, that's for another time. So if that be the case, look at that first row. That first row says x plus, that would be z, but z is now a, is equal to 3. So that means that x is equal to 3 minus a. Look at the second row, and we have y minus, it would be z, but that's now a, is equal to 1. So y is equal to 1 plus a. And from there you can see how we end up with that solution. Now let's continue. Let's look at the next problem. Oh, that note there at the bottom is important. That's the theorem. The number of parameters of an infinite solution set equals the number of unknowns, that is variables, minus the number of equations. And that's something that I told you there before. How many parameters do you have? Well, you take the number of variables minus the number of equations, and that gives you, for this particular problem, that would be 3 minus 2. Those 3 equations reduce to 2 equations, 2 rows. So we have 2 rows but have 3 unknowns, x, y, z. So 3 minus 2 is 1. So that's why we only have let z equal to a. And then x and y depend on z. Thus we have a dependent system. Now maybe I got ahead of myself, and that's okay, but here is the main system strategy that we use to solving systems. For the previous problem, after you have reduced the system, notice that, well, I just said that, but anyway, Gauss-Jordan. To put a system in reduced row echelon form, here, reduced row echelon form is the same terminology for Gauss-Jordan. Gauss-Jordan means reduced row echelon form. Gaussian elimination is the same as row echelon form. Row echelon form is basically where you have terms along the main diagonal and zeros below it, and then you use back substitution to solve the system, to finish solving the system. For reduced row echelon, think about that. That kind of begs what it means. If you have row echelon, you want to reduce that even further. Well, that simply means here that our goal is to get ones along the main diagonal here, and then we want to get zeros elsewhere. Now this scheme that I have below that I would show you illustrates the strategy. Now notice that the subscripts represents the number of rows and columns. Always the row first, next the column. So this is row 1, row 2, row 3. I have that down below. Let me pull that. So this is A11, first row, first column. Here A12 is the first row, second column, and so on. So with that, these steps that I list are in the general sense Gauss-Jordan. So use the elementary row operations to first get a 1 at A11, that's here, and then use that 1 to get zeros below it, right, at A21 and A31. That's step number 3. Well, step number 2, excuse me. Step number 3, we want to get a 1 at A22. And then step number 4, use that 1 at A22 to get zeros above it and below it. I was doing that for that previous problem that I just got through working, right? And then after that, step number 5, get a 1 at A33 and then get zeros above it by using that 1. And how do we do that? We use those 3 elementary row operations. You can interchange rows. You can multiply any row by a non-zero scalar or non-zero number, and then you can add a multiple of one row to another row. Let's see. Here in each part, suppose that the augmented matrix, what does that mean, augmented? It's a line there, right? Has been reduced by row operations to the given row echelon form. Here, solve the system. I'm going to finish solving. It's in row echelon form, but I want, and now you want, reduced row echelon form. So we're going to use this one. Notice that first column is set for us, so I come to the second column, I go to A22, and now I want to get a 0 above it. We already have a 0 below it, so we'll say here 3 times row 2 plus row 1. Now I'm going to go ahead and just rewrite rows 2 and 3. So this is a 1, that's a 0. This is 6 plus 4 is 10. That's the 3 times the 2 is 6 plus 4 is 10. And then 3 times the 2 is 6 plus this 7 is 13. And so now we're going to use the 1 at A33 to get zeros above it. To do that, we're going to simply say negative 10 times row 3 plus row 1, and then negative 2 times row 3 plus row 2. Now we get this reduced row echelon form here. That 5 stays the same. Now let's go back. Negative 10 times this 5 is negative 50, plus 13 is negative 37, and then negative 2 times 5 is negative 10, plus 8 is negative 8. Now once you reduce that, you look at it, and what that says is 1 times x, so 1 is equal to negative 37. So this implies that x sub 1 is negative 37, x sub 2, 1 times x sub 2 is equal to negative 8, and then x sub 3 is equal to 5. And you get that solution there. Okay, this one is in row echelon form. So let's see. Now come here to that first column. I have 1, and then below that, I have zeros. I go to the second column and I find A22. They have zeros above it and below it already. Now I want to come to A33, and then I want to get zeros above it. To do that, we would say -8 times row 3 plus row 1, and then -4 times row 3 plus row 2. All right. So row 1 and row 2 are changing, so let's just rewrite row 3. So -8 times row 3 plus row 1. So here this 1 stays there. That's a 0. We get -8 plus 8 is 0. -8 minus 5 is -13. -8 times 2 is -16 plus 6 is -10. -4 times row 3 plus row 2. So this is 0, 1, 0. And then this is -4 minus 9 is -13. -4 times 2 is -8 plus 3 is -5. Now there's nothing else that we can do. Look at the main diagonal. The main diagonal is here. Now watch this. I have 1, 2, 3, 4. I have 4 unknowns. And I have 1, 2, 3 equations. So you remember that says that 4 minus 3 equals to 1 parameter. What's the parameter? It's going to be this last guy over here, because if this was a 4 by 4, 4 rows and 4 columns, then there'll be a number here, maybe, and hopefully it won't be 0, that you could reduce the terms above. But I don't have that last row down there. But notice that for row 1, it has a x sub 4 in it. Row 2 has an x sub 4 in it. Row 3 has an x sub 4. You see how all the variables depend on x sub 4. So let x sub 4 equal to t. Now you should be able to look at it and kind of tell what's happening. This says x sub 1 minus 13t is equal to -10. That means x sub 1 is equal to 13t minus 10. That second row says x sub 2 minus 13t is equal to -5. So we get x sub 2 is equal to 13t minus 5. And then the last row says x sub 3 plus x sub 4 is equal to 2. Well, x sub 4, you remember, is t. So x sub 3 is equal to 2 minus t. Well, we should have everything we need. And that should match up with what we have there. 13t minus 10 for x sub 1, 13t minus 5 for x sub 2, 2 minus t for x sub 3, and then a t for x sub 4. Now I'm putting the solutions over here. We don't know that it's a solution, but you do know by looking at this that it's that the solution is inconsistent. That inconsistent statement means there's no solution. Because of that last row, that really says 0 is equal to 1. If you interpret the first row, that's x sub 1 minus 3 times x sub 2 plus 7 x sub 3 is equal to 1. That second row says x sub 2 plus 4x sub 3 is equal to 0. That last row says 0 is equal to 1. That is impossible. So that's why we have no solution. That's a K or a kappa or a it's the Greek letter, a K, yes. But no, it's just impossible. Let's see if we can get this one. So I'm going to write this as a matrix. So 1, 1, 2, 8, negative 1, negative 2, 3, 1, 3, negative 7, 4, and 10. So we want to have a 1 at A11. We got that. Use that one to get zeros below it. To do that, we just simply say, just add row 1 to row 2. This guy's already a negative. So row 1 plus row 2, and then negative 3 times row 1 plus row 3. So this is 1, 1, 2, and 8, which is adding row 2 to row 3. Negative 1, 5, and 9. Negative 3 times row 1 plus row 3, so that's a 0 there. Negative 3 and negative 7. Negative 10. We get negative 6 and 4. That's negative 2. We get negative 24 and 10. It's negative 14. Now we move to the second column, and we want to get a 1 at A22. It's negative 1. I mean, it's okay for right now. So what I'm going to do is you take that 1 at A22 to get a 0 above it and below it. So what I'm going to do for right now is add row 2 to row 1. This is 1, 0, 7, 17, 0. And if it's okay, I'm going to do a couple of things here. I'm just going to multiply a negative times row 2, and then that'll give me the 1. Negative 5, negative 9. And I kind of want to go ahead and just let's work the problem. This last row, if I multiply by a negative 1/2, at least that can reduce these numbers because they're all divisible by a negative 2. Okay. So now we use the leading one at A22 to get a 0 below it. So we do that by saying negative 5 times row 2 plus row 3. There's 0 there, 0 there. We get 25 plus 1 is 26. We get 45 plus 7 is 52. So now we'll say we need to get a 1 at A33. So 1 divided by 26 times row 3. This is 1, 0, 7, 17, 0, 1, negative 5, negative 9, 0, 0, 1. And that's divisible by a 26. Thank goodness for that, right? So now we use A33, which is a 1, we call a leading one, to get zeros above it. To do that, we'll say negative 7 times row 3 plus row 1, and then 5 times row 3 plus row 2. Well, that'll give us, we call this later on the identity matrix. Now we do the work, do the math over here on the augmented part. So negative 7 times 2 is negative 14 plus 17 is just 3. And then 5 times 2 is 10 minus 9 is 1. And so that implies that the solution is 3 comma 1 comma 2. And that's what we have up there. Let's see this one. I'm going to write this as a matrix. Now we want to get a 1 at A1, 1, but let's just use the two-side advantage since everything in the column is divisible by 2. So we can just add row 1 to row 2 and then say negative 4 times row 1 plus row 3. So this is 2, 2, 2, 0. We're adding rows 1 to 2, 7, 4, and 1. And then negative 4 times row 1 plus row 3. So that's the 0 for the first one. Negative 8 plus 1 is negative 7. Then we get negative 8 plus 4 is negative 4. And then we say negative 4 times 0 is 0 plus a negative 1 is negative 1. Now notice that rows 2 and 3 are multiples of each other. That tells us that you're going to have infinitely many solutions, because once you, for here, add row 2 to row 3, you're going to cancel out row 3. So row 2 plus row 3. And while we're here, I mean, let's just go ahead and just divide everything in row 1 by a 2. So 1/2 times row 1. This is 0, 0, 0, 0. Remember, an entire row of zeros begs for infinitely many solution. If there's a number in the augmented part, if you got zeros on the left side and you have a number other than 0 right here, then you know that you have no solution. If there's no solution, you stop. But if you have an entire row of zeros, including the augmented part, you have to solve for the solution, the infinite solution set. And we're going to keep reducing this, because where that 7 is for Gauss-Jordan, you want to have a leading 1 there and then use that leading 1 at A22 to get a 0 above it. To get a 1 where that 7 is, we're going to just divide row 2 by 7. And we get some fractions. We don't really care for fractions, but it's a part of life. So now we use the 1 at A22 to get a 0 above it. So we say negative times row 2 plus row 1. So I'm going to rewrite rows 2 and 3. So 0 there. So this is negative 4 over 7 plus 1. So that's negative 4 over 7 plus 7 over 7. So we get 3 over 7. And then negative times 1 over 7 is negative 1/7 plus 0 is negative 1/7. So notice at this particular spot is where we have the 0 on the main diagonal, right? It's the main diagonal. So wherever you have that 0 on the main diagonal, that's the parameter that you let to be the that's the variable that you let to be the parameter. So if you call it t, let x sub 3 equal to t. Yeah, you can look at it now and tell x sub 1 is negative 1/7 minus 3 over 7 times t. That's that first row. Second row is x sub 2 is equal to 1/7 minus 4 over 7 t. And so you get all three of those solutions there. Well, you get the one solution that has three parts to it. Just like you consist of a body, a psyche, it's a mind, and then a soul, right? So, well, excuse me, a spirit. Soul and psyche is the same thing. So there you go. You have three parts that you consist of, and likewise a point. And so, what's your point? Okay, why is this no solution? I don't know. We have to do the work. Let's write this as a matrix. This is 0, negative 2, 3, and 1. This is 3, 6, negative 3, negative 2. 6, 6, 3, and 5. Okay. So, let's see. We have a 0 there. I mean, that's okay. You know, you want the leading 1 at A11. But we can always interchange rows and you can get what you need. Let's use this 3 to get a 0 where that 6 is. So we'll say negative 2 times row 2 plus row 3. Hopefully you didn't hear that. There's a bomb or something dropped. But anyway, 0, negative 2, 3, and 1. This is 3, 6, negative 3, negative 2. So we're saying negative 2 times row 2 plus row 3, so that's the 0. We get negative 12 plus 6 is negative 6. And so sometimes, you know, you might not be able to just look at it and tell that it's going to be that. You have to do some work, right? There's nothing wrong with work. So negative 2 times negative 3 is 6 plus 3 is 9. Then negative 2 times this negative 2 is 4 plus 5. We get 9. Now, I'm looking at rows 1 and rows 3. This is negative 2 and 3. It's multiple of the negative 6 and 9, right? So what I'm going to do is and I know we're kind of going out of order, but right now I just want to reduce the dang on thing. So I'm going to use this negative 2 to get a 0 there. Now when I cancel this guy out, I'm going to automatically cancel this out, and something strange is going to happen over there. So here we'll say negative 3 times row 1 plus row 3. This is 0, 0, 0, if I'm doing that right. So it's negative 3, negative 2 is 6 plus minus 6 is 0. We get negative 9 minus 9 is 0. And then we get negative 3 plus 9 is 6. Uh-oh, that's no solution, right? Here, this says that 0 is equal to 6. impossible. If only I could write M. You know, it's hard for me to write crooked things like an M because my hand is crooked. So no solution. M, I, crooked letter, I, crooked letter, I, humpback, I. Was that that? Okay. So here's a theorem. If the number of unknowns outweighs the number of equations, then the solution set is non-trivial. Look at number 7 down here below. So I have 1, 2, 3, 4. I have 4 variables, 4 unknowns, and then I have 3 equations. So if the number of variables outweigh the number of equations, then automatically I have the non-trivial solution. The non-trivial solution is the infinite solution set. We call the infinite many solution set the non-trivial solution. Here's a corollary that's no more than just a minor consequence theorem that is correlated to another theorem. This says that an n by n linear homogeneous system, n by n meaning the number of rows is the same number for the number of columns. If I have 3 columns, I have 3 rows. You know, and columns represents the number of unknowns, and the number of rows represent the number of equations. So if you have the same number of equations as you do the number of unknowns, and if it's homogeneous, homogeneous means that the augmentation are all 0 terms. Each equation is set to equal to 0. We call that a homogeneous equation. And if it's a system like that, then we call that a homogeneous system. If it's an n by n homogeneous system, then you always have the trivial solution. That is that each variable it will be equal to 0. Look at number 8. Number 8 here, this is an n by n. I have 3 unknowns and 3 equations. It's homogeneous, right? Because all the terms are equal to 0. And so the trivial solution is x sub 1 is 0, x sub 2 is 0, and x sub 3 is 0. So I'm giving you some fuel so that some of the problems you might not even have to work if you know what's going on. Number 9, you have 3 unknowns and 2 equations, and so there you have the non-trivial solution. Number 10, you may say, no, I have 2 equations and 2 unknowns, but if you look closely, equation 1 is a multiple of equation 2, right? They differ by the factor of a 2. So really you're only talking about just one equation. You're only talking about 3x sub 1 minus 2 x sub 2 equal to 0. It's only one equation. Okay. So you got here one equation, 2 unknowns, right? So 2 unknowns, 1 equation, 2 minus 1 gives you 1 parameter. That means that one variable depends on the other. Non-trivial solution. Solve the system by any method. Is homogeneous, and it's square. The number of rows equal the number of columns. Automatically trivial solution. Same thing for this problem here. Yep. I think that'll do it.